Hi, my name is Anya Zhang, and this is my Lab 5 demonstrating collisions. In this presentation, we're going to go over an introduction, my procedure, results, errors, and a conclusion. In this lab, we're going to compare observed and predicted trajectories, energies, and momentums of a collision. We're going to do this using Tracker, which will have our observed data, through GlowScript, which will be our computational model, and then our objects are going to be two billiard balls. This will demonstrate the conservation of momentum. So how does it work? The most important concept this lab is demonstrating is the conservation of momentum. It states that the initial and final momentums are equal, so the change in momentum is zero. Momentum is also equal to the mass times velocity, so the equation can be further specified as the mass of the first ball times its velocity before the collision is equal to the mass of the second ball times its velocity after the collision. For our velocity update formula, our F net is contact force that is felt instantaneously and the only force felt. This isn't the typical application for the velocity update, as it isn't used for the entire duration, but just the collision part. For my procedure, the first thing I did was to find the video of two billiard balls colliding. Then I used Tracker to create a data set of the markers using position versus time. So this is our observed data. Then I created a computational model in GlowScript that predicted kinetic energy and momentum before and after the collision. From there, I analyzed and drew conclusions. So here's our data. As I said in the beginning, for this lab, I found a video online of two of the balls colliding. From there, I used Tracker to plot points and velocities, which I then used to create my computational model in GlowScript. Okay, so here's our code using the data we collected from the video. The first thing I did was just define everything, including the billiard balls and their components. This includes mass, time, positions, velocities, energies, momentums, and such. From there, we move into our loop that detects whether there is a collision based on the distance of the balls becoming less than the diameter of either ball. If a collision is detected, the code inputs a contact force that affects each ball in equal and opposite forces. Then, we just update the positions and the momentums for each time step. The last thing I did was to create graphs of the kinetic energies and momentums for each time step to help visualize the concept of collisions. We can see that the collision wasn't totally elastic as the energies did not transfer perfectly, but momentum is conserved as the text box shows, even if the momentum graph doesn't look conserved. Ultimately, the basis of collisions demonstrates that the conservation of momentum, as all collisions should have the initial and final values of momentum equal, as we can see a near-perfect transfer in the graphs. In both the observed and computational models, we can see that the collision isn't totally elastic, and that can be accounted for through various errors. This includes human error in calibrating Tracker, estimating distances, being imprecise in defining center of masses and such, or external forces such as friction and the person's hand manipulating the ball. Lastly, the video itself wasn't totally straight, so the distances and offsets would not be totally accurate either. Here are some additional questions. What if the collision is elastic? In an elastic collision, the kinetic energy should transfer completely, although my computational model wasn't perfect. That means that the first billiard ball would have stopped and the second one would have the same velocity as the first one, magnitude-wise. 2. What are some examples of where energies could have gone in an inelastic collision? Due to the energy principle, change in energy will always be zero. Since the collision is not elastic, the change in kinetic energy isn't zero. So where does it go? Some examples are sound, material deformation, internal energy changes such as rotation and vibration too. Overall, through this lab, we demonstrated using collisions the conservation of momentum. By creating a computational model, we could visualize inelastic collisions and the transfers of energy. Thanks for watching.